Thanks for the introduction. Indeed, Ruben and I know each other, I guess, from the start of Jets, whichever you would like. I myself am a professor at Jets, professor at the University of Tilburg in data science. I work a lot on bandits, contextual bandits, and that's what I talked about 2 years ago. And I think also 2 years ago, I very briefly talked that we were in some ways entertaining this idea of starting a startup that ended up being called Scalable. And we did, basically. So 2 years ago, we started up. By now, we have some funding. We grew the team to about, 8 people right now. So we're kind of growing. And I want to share a bit of what we're doing, why we're doing it, and get some feedback there. So that's mainly the topic of the talk. I was expecting more of this kind of button thing. Let's see. I should point it in that direction. I'm really trying. The way around. This is pretty impressive. There's people upstairs that can probably go to the next slide. Oh no, there's like a bunch of stress, people running around. My first slide was a bit of background about myself, by the way. So I already briefly introduced myself. I'm just going to keep trying to actually get this going. Yeah, it's nicer to have some pictures. We'll see what happens. None yet. But let me just dig into the topic. So what I wanted to talk about today is kind of why we started working on Scalable, and what we're trying to do with Scalable is what I would call applied AI on the edge, why we're doing this, and kind of why, in some ways, we started building the technology that we ended up building. I'm still trying to do this button, but it's still not working. And I want to first share, effectively, kind of a few projects that I've worked on myself over the last few years that, in one way or another, effectively failed. So these were, These were all data science projects, basically, that I have worked on, and that we managed to take up to some level, but then failed. And those failures, in some ways, are the failures that we're trying to solve with the company. Still no. So we're just going to talk about these. Ooh, interesting. Yeah, so here on this plot, no, no clue. But I'm just going to talk about these 4 projects and dig right in and ignore these slides. And once the slides are up, we'll get back to them. So kind of over the last, I would say, 10, 15 years, I did my PhD about 15 years ago, 12 years ago. I've worked in various positions kind of in data science, both in academia and in industry. And a number of projects, I would say, that I've worked on, which are in very diverse fields, which in some ways I think is one of the awesome things about working in data science, is that you can work in very diverse fields. Work, for example, in e-commerce, or work in healthcare, or work in industry, and actually have kind of an extremely diverse palette, basically, of projects that you can work on, which I have, but I've worked, and I've just picked out 4 projects, which, were supposed to be on this slide in some way. I've picked out these 4 projects that we managed to take very far, but in one way or another failed. And the first one is one that I started 10 years ago, and that started, that became kind of known as this idea of what we started calling persuasion profiling. And it was basically an idea of how to build up e-commerce pages to become more effective. So this is also where a lot of my bandit work and stuff came from. It's like, oh, you have this page, how do you build it up? If you have loads of variations of this web page, how do you build it up in a sense, such that you gain as many clicks as possible? And that was kind of some of the work that I've done in my PhD. It's kind of considering different algorithms to actually build up these pages. And then we spun out, started a company doing this, and we were able to show that based on effectively randomized data, we could do offline performance evaluations of these different algorithms, and we could show that we could increase click-through rates by quite a large margin, basically. So there we had this project that we done a bunch of data collection, a bunch of modeling, and we had models that, in effect, on the data that we have, we could show that we were able to, in some ways, increase the business goals. So this was this thing I skipped over on my introduction. Fine. Here are some of the projects. So I haven't gotten very far in the talk yet. First project that somewhat failed was this kind of recommender system in e-commerce. it worked fairly well on the offline data. We never got to implement it truly. We collaborated with Booking.com at the time, which was still a cool company at the time. I don't know if I can say these kind of things. But in any case, we collaborated with them, and we ended up not necessarily implementing that algorithm on their live web page because we were unable to compute what the next website page should look like quickly enough before the next page should be served. So we ended up implementing some of this on their email marketing campaigns, which are obviously slower, and we had time to compute. But we didn't actually get to the point of actually putting it live. And some of these other projects, although they're very, very different in nature, all kind of essentially share the same structure in the sense that after working with this e-commerce project, I've worked for quite a long time together with IKNL. IKNL maintains the Dutch Cancer Registry, so they have a lot of data of virtually anyone who's ever had cancerous cells in their body in the Netherlands. We worked on prediction models for adjuvant chemotherapy, so whether or not somebody should get chemotherapy after after getting surgery for colon cancer. We created, I would say, very appealing models, even kind of understandable ones, also relating to the previous topic. We showed on a bunch of the already existing data that we were able to make better kind of individualized choices, and in some ways, like at least in expectation, increased life expectancy. That model, again, I think, as with the first e-commerce one, it's a useful model. We managed to validate it. We never managed to take it all the way to actual production in the hospital. Why not? Well, for some of the issues that were already in the previous talk, because it's just inherently very hard to be in healthcare. We also suffered from a lot of issues of data privacy in the end. So we had all of this set up on servers. We wanted to have just people send over kind of patient data. We would, compute what the next advice should be, and this kind of stalled. And we've been searching for ways of getting these models into the hospitals as opposed to actually like sending the data out to us. Another project, we did something together with a large consultancy firm in the Netherlands, monitoring the behavior of animals in slaughterhouses. It's not the nicest videos, really. But there we tried to make models to see if, in the end, some of the pigs were mistreated, basically. And there as well, we kind of created a bunch of useful models on a lot of their offline data, created, or were able to show that these worked, never got them into production. Why not? Because actually, like, streaming all of this data to the cloud proved to be quite tricky and predominantly quite expensive for them. Final project, more recently, that hasn't filled yet. I think we're still working on it. It's kind of the upper right, working on trying to predict how much food a cow should get, and it's kind of these robots are actually delivering this food to these cows. Here we have pretty good prediction models as well, based on a bunch of offline data, but now it's kind of tricky that most of these robots do not have a stable internet connection to actually get any of these predictions from the cloud, and then it's kind of how do we maintain and make sure that these models are running, in a sense, on the robots themselves. So these are just a bunch of projects that I've worked on myself that, in some ways were successful because we created cool models, we were able to show that they were doing well, but none of them actually made it into production in the way we'd like them to be in production, being used at an extremely large scale. And I think a lot of that is kind of due to kind of how we ended up, maybe even culturally, creating these types of applications, and then how creating them might differ from actually using them. So how creating such a model differs from actually using such a model. So I think it's useful to kind of, and I know this is kind of high level, I'll get into some of the nitty-gritty at some point, but to kind of look at how all of these projects, despite the fact that they are in very different fields, in some ways came about. And if you look at that, basically what you see, and I think this is kind of by and large true for any machine learning AI process, we go through these stages of, in some ways, first making sure we have data. I think actually a lot of projects actually end there. There's no data, the data quality is not good enough, whatever. This is where the problems are, basically. Once you have those, and in all of the 4 problems that I was just talking about, we actually had a bunch of access to high-quality data. And so we made it to this next step, which I would call predominantly data analytics. It's really fitting models, but it's trying to understand what's happening in this data. And to be fair, I think a lot of AI machine learning projects rightfully, in some ways, stop at that stage. And this is even likely to happen for this EKNL, like colon cancer work that we did. So despite the fact that we never managed to actually run these models in the hospital, which would have been, in some ways, our dream when we started this project, by understanding some of that data and analyzing some of that data, we now do know that for specific types of tumors, there's a lot of uncertainty about the effectiveness of this kind of adjuvant chemotherapy, and it's fairly likely that we'll be setting up new kind of randomized controlled trials for those specific groups of patients to learn more about the effect of the intervention. So now we've analyzed that data, and we took some knowledge from that data, and that is really kind of the tangible result of our projects. However, you can go one step further in many of these projects, where you're actually not just understanding this data, but you're creating models, often kind of prediction models, that, for example, would predict how to build up the next page. And those you can evaluate on offline data. So you can evaluate your bandit policy on offline data, which is what we did in this e-commerce setting. And then too many projects, and maybe some of you have been in some of these projects, basically end there saying like, oh, we have this model, and kind of on the historical data that we have, it is pretty cool. It works well, it predicts well, we can make better choices, basically. Regretfully, a lot of projects, I would say, stop there. Where all of the projects that I've just talked about in some ways failed is this last step of then, once we have a model that's not just in some ways data analysis, but really it's doing something autonomously, it's predicting something, it's generating its own kind of advices on what to do, to actually move that to large-scale usage. So now all of these decisions would be automated, that this model is actually in play, there's no more humans looking at it, it's actually running. To actually get to that last point, that's where all of these 4 projects failed. And that was kind of the idea that a lot of these projects failed was kind of the backdrop for what we try to start doing with the company. But I think to kind of understand why, at least in my perception, and maybe you don't share it, I'm happy to hear any comments kind of after this talk, why in my perception a lot of projects find it very hard to make the step from kind of the model creation to the actual model usage, is because if you think about how we actually often intend to use AI, and again, I think this fairly often is kind of culturally driven how we try to use these models, is that what we try to do is we do the first few steps of this little pipeline kind of in a cloud environment. So we have our sensors, which are kind of in this e-commerce projects, those were just the web pages, so that's the browsers of people. In this kind of slaughterhouse, big animal monitoring projects, with a bunch of cameras. In the EKNL projects, it's actually the electronic patient records that are running in the hospital. So it's all of these kind of distributed places where this data is collected. We're sending all of that data to a central place, to our cloud, and this is where we're doing all of this data analysis, basically. And I think this is what most of you are fairly used to have some way of accessing the data in a central place, fitting models to it, understanding what is coming out of these models, so doing your data analysis, and maybe even kind of seeing how well these models perform on this offline data that you have. But by the time you then actually want to use a model like this on a very large scale, and let's just zoom in on this kind of animal behavior project that I was just talking about. So this is data of pigs being filmed as they're walking into a slaughterhouse. And basically what it's trying to do is trying to see whether these pigs are mistreated. And one of the kind of things that it's trying to recognize is whether there's enough space between the pigs. Sorry for this kind of, maybe too lively example. But that's kind of what's happening. So they have a bunch of data there that these models were trained on. And initially what they were trying to do is effectively do this round trip, also when basically after fitting the model. So we've fitted this model, we can predict whether there's too little distance between these pigs, and now we're gonna have multiple of these live camera streams that are being streamed up to our, in some of this Microsoft Cloud in this case, where we're running these models, and then the results are gonna be fed back to this slaughterhouse to actually kind of maybe intervene if something is going wrong. So that round trip proved to be extremely expensive. It also proved to be way too slow in these cases. And there, I think, was in some ways, maybe stupidly, but one of my first kind of encounters with this idea of why not, after finishing this model training bit, so after you have a model that works well, why not just move it downwards, move it to the location, have it run as close as possible to where that data is generated and where the results are actually necessary. And this is, in some ways, what I try to allude to with my title of this talk of applied edge AI. It's kind of moving some of these models, whether they are AI or machine learning, whatever you want to call them, and some of these models that actually automate some tasks. So I'm not talking about training models. I'm really talking about once you have a model that, for example, recognizes, is there too much distance between these pigs, or that recognizes how much food should this cow get, or that kind of recognizes this specific patient should get chemotherapy. Yes or no. So I've trained this model. Now I'm thinking about using it at a large scale. Why not use it by pushing it down kind of to where the data is generated as much as possible? No? Why is that a reasonable thing to do? I think there's many advantages of doing this. So moving these trained models to what we're calling the edge, so closer to where the data is generated, effectively leads to higher just inference speed, because you don't have any network latency and these kind of things. It often leads to cost savings. You don't have your cloud costs. You can often run stuff on devices that are already on a location. I also do think, actually, a lot of people really overestimate how many computational resources are necessary to run, for example, relatively complex vision models. So even these models that are trained to see how far these pigs are apart, we can run them on basically industrial gateways that have some processing on them. So we don't need large GPUs to run any of these models. By the time you've actually trained that model and really tried to condense it, we can run it on fairly small hardware, I would say. So you can push it down, reduce the cost. You can make sure that your data doesn't leave the site. So in a sense, increase the privacy, especially when this is data of people or when you're filming people, for example. Even with kind of GDPR type rules, it is even in many cases just impossible to send like live data streams to your cloud. So processing on location is appealing. And you save a bunch of energy by not having all the data move back and forth, basically. So there's, I would say, and this is something that I kind of didn't know about at all when I started just doing all this bandit stuff on the cloud, but by moving more and more to these kind of vision applications on location, to these healthcare applications, kind of became aware of the, I would say, large advantages of moving some of these models down to kind of closer and closer to where the data is generated. And again, I'm not trying to say that this will be suitable for any AI or machine learning project. I'm just trying to argue that there are such projects, and there's quite a large class of projects, I would say. A lot of vision projects, for example, would actually benefit from moving that processing down after your model has been trained, instead of actually moving all of your data up to the cloud. Now, I hope that somewhat makes sense, but then if it does, you can immediately start to wonder, like, why isn't this happening at an extremely large scale? Why isn't this, like, common to just move all of these models to the edge? And I would say, well, there's two responses to that. One is, it is getting more and more common. So there's a big stream on kind of tiny ML, people moving machine learning models to kind of small MCUs, to moving them to edge devices. This kind of whole edge AI idea, I think, is really kind of growing, and there's more and more companies in that space. So we hope we'll survive, basically. We moved into the space, and we now see it kind of exploding. But the other end of things is that it is fairly challenging to actually move these models to these edge devices. And why is it challenging? I think that the easiest kind of way of thinking about why it's challenging is because the edge is much more diverse than your cloud is. Like, the edge is a whole collection of all kinds of different devices that are there predominantly because they're often already doing something else. So these gateways might already be, doing their gateway stuff. They might have very different processors, so you might have been training on your Intel stack, and now you want to move this model to like an ARM 32-bits device, basically, or even to a smaller MCU. So you now have to think about, how do I cross-compile these models? Maybe just using your kind of containerized setup that we're very used to in the cloud will not actually work on these devices, because even kind of your standard Docker container would give you like 1 gigabyte of overhead, I would say, just memory-wise, which is very hard to actually push to some of these smaller devices. So you get into a lot of, I would say, in the end, kind of engineering challenges, but you also have to understand very well kind of the models that you're fitting if you want to overcome these engineering challenges, because obviously the more kind of compressed or the more concise you can specify your model, the easier it might be to actually move it to these devices. So I think really, there's this kind of idea of moving these trained models to these edge devices, that idea is reasonable for various reasons, but now it becomes a technical challenge of actually doing that well. And that's some of the stuff that we've tried to work on, basically. And I'm just going to spell out some of the things we do to actually make some of these projects work and make some of these projects move to the edge. It is definitely not the only way you can go about. There's more kind of unfolding. This is really a moving kind of field, I would say. So there's more and more players in that field that are exploring different solutions. I'm just going to say what we do, because I know what we do. But again, if you're interested in this edge AI field, make sure to kind of explore that whole space, I would say. But effectively, what we do is kind of on this image. What we do is we take effectively models. So often we're kind of interacting with people that are on the left side of this plot. It would be kind of a data science team, people creating these models. Whereas on the right side, it would be often kind of this embedded systems team or people that are maintaining the actual hardware, that are maintaining kind of the infrastructure that's there on location. So we're moving between these two kind of teams or different roles in a sense. And what we do is we heavily rely on what's called ONNX. ONNX, I don't know how people pronounce it. Who knows of ONNX? Let's use it at all. I'll have a few slides on it. It's basically a way of storing a model. It's slightly more broad. Actually, it's storing a whole kind of data processing pipeline in a standardized way. The nice thing about this is that it's not an implementation of that pipeline. It's just a description of that pipeline, which then you can still kind of operationalize in pretty much any platform that you want. So now you have a platform-independent way of storing all of the operations that need to be done to come from the desired input to the desired output. And if you just think about what is actually happening, for example, in that kind of animal welfare project, it's just images of pigs, so that's your input, and the output is, are they too close together, yes or no, basically. The logic in between is something you could specify in ONNX. You can describe how to convert this input to this output without actually having an implementation of it. So it's not an executable, it's a description of how you would build something that can be executed to turn the desired input into the output. Hope that was not too abstract, but kind of what it's trying to do. What we then do is we take that and we convert it to WebAssembly. WebAssembly is kind of this, one way of thinking about it, it's intermediate representation that normally you would go through if you're trying to compile these things, like if you're compiling an application, but that's optimized for portability. What does that mean? Basically, it means that we can run on the device a very small, what we call runtime. It's a very small bit of software that is compiled for that specific device. So whether that's an MCU or an ARM chip or an Intel chip, it's a very small bit of software. It's very small. It has 65 KB of memory footprint in kind of a small. So it's really a very different beast kind of compared to any kind of containerized solution. And that can run this WebAssembly binary, basically. So now I have this portable thing that is just describing my pipeline, nothing else, that I can move to this device and run it. Now, obviously, on the device, you'll need to code around to actually make sure that the input and output are correct and whatever that that the data is being passed to wherever you want to pass it. But this is kind of the basic of what we do. We take kind of stored model pipelines, convert to WebAssembly, and push them to these devices and make it possible to kind of push them basically to coordinate which device runs which model and kind of try to solve all of those hurdles in between. I think generally, if this is not of interest to you at all, great, or not great. It's only 5 more minutes, so you'll survive, let's just put it that way. But I do think you want to look a bit at what this ONNX is. It started, I think, 2-3 years ago. People started developing it, predominantly driven by people from Microsoft, but it is now really rapidly growing, I would say, that ecosystem. And in the end, ONNX just specifies kind of the computation, so the operations that you want to do on some input to produce some desired output as this kind of directed acyclic graph with operators. So operators might just be like add to tensors that are coming in, and kind of the edges in this graph being the tensors, so the kind of generalizations of vectors, matrix, tensors, fine. The data that's being flowing, that's kind of moving from one operator to the other. Yeah? So ONNX is just a description of this. It's a description in protobuf, doesn't really matter in this case, but it's just a description of, given my input, what operations do I do to create the desired output. And this might look very simple, but you can have actually like very complex, like deep neural networks, you can specify this way. And there's this set of operators that's available. You can even create your own, but I think the selected set is very broad and very expressive. So you can create these graphs and effectively store fitted models, also store full data processing pipelines. So a bunch of pre and post processing you can just add to this ONNX graph. And now you have a representation, and what I really think is important about this, now you have a representation of your learned model, full pipeline, that is not tied to your infrastructure at all, basically. So now you have a way of even like storing and versioning fitted models and fitted pipelines. Then if you move from your Python stack to whatever else you want to move to, that at least you have kind of this single source of truth of what your models should do. So I think ONNX as a tool for just more generally data scientists is extremely awesome. We're happy we're looking at it. It's a bit challenging to work with, although things like PyTorch, TensorFlow will just readily export to ONNX, basically, so you can just save things in ONNX format. But if you want to kind of edit some of these graphs and edit some of the pre and post processing, it's possible. It takes a bit of getting used to, but we ended up generating, I'm just going to skip through a bunch of these slides, but we ended up generating a bunch of Python tools to actually do this. So if you ever want to work with ONNX, we've open sourced a bunch of our tooling, and effectively, if you want to manipulate these graphs to add like pre and post processing, play around. Admittedly here as well, this is an open ecosystem, it's growing. There's a few packages out there that are trying to combine like some of these functionalities of ONNX. Not sure if this one will be the one surviving. We'll see. I hope somebody at some point just pushes together all the tooling that is there to make it really accessible. But we are able, which I think is kind of cool, to use ONNX to really kind of construct, just through very, very simple Python syntax, constructs our own pipelines from scratch. And that makes it possible to do things like this, basically, which I think is kind of cool. That right now you can just say, look, I want to like identify, count, recognize, know where specific objects are. I just want to count the number of cars. Fine, if somebody does a query like this, we can spit out an ONNX model that, given that it's fed an image, will give you the count of the number of cars that's there, basically. And that model, we can then kind of compile to WebAssembly and just send to whatever kind of edge device that we want. So we're really reaping kind of these benefits of this flexibility of ONNX to kind of construct not just a model, because like one of the things we would be using here is just like a YOLO V5 model or something as kind of the base model. We're just adding some pre and post processing to it to make it functioning for something that somebody actually wants, and then move that to this edge device. I am almost running out of time, so I'm going to skip through a few things here. We tried to patent this. We'll see how that goes. But effectively, what we ended up doing is implementing all of this on a bunch of edge devices. We are heavily collaborating at this moment with Advanter. Do people know Advanter? Kind of interesting. They're like the largest manufacturer of industrial routers and gateways in the world. So they're actually a fairly big Taiwanese company. And they build, like they ship these kind of blue boxes, but they ship all kinds of things. They make industrial PCs and these kind of things. They're really big in that market. And they are right now shipping, well, these small blue boxes here that are on the lower right with our runtime pre-installed. So effectively, the software that can basically eat up this WebAssembly packet is already on that router. Even more, we've kind of made it such that you can basically just configure the cameras that you're attaching to it, and the REST endpoint, or Modbus, or kind of whatever format that you want to send the results to. And then you can just download a model and run it on that device. So effectively, if I go back here, what we really try to do is, together with them, is take away all of the engineering on that side, basically. Make all of that just configurable. The only thing people need to do is create a model, and can just push it to that device. So then we have these kind of kits. You can just configure on the router itself. So this is just a router installation menu. You can do this with configs as well. But effectively, you can just push these models directly to, for example, a gateway, run up to 4 cameras, and do things like license plate recognition, or count the number of people, or see whether there's enough distance between people, which suddenly becomes topical again, or count the number of bikes, or like any kind of vision model, I guess. Well, not any. Many vision models that you can envision, we can actually run these routers, with obvious limits, because if some of them are too large, these routers, the one I was just showing, that's an ARM 32-bit chip. It is reasonably fast. We can run, like for ANPR, for example, we can do about 12 frames a second to recognize license plates. If you want to be much faster than that, or if you have much larger models, okay, at some point, you're just, basically the capacity of the device you'll run out. And this is, again, some of the challenges is in making sure that you have a model that once you push it to a device, that you know how well it's going to work on that device, that you can predict like how much resources it's going to take, how fast it's going to run, where it's going to run, and that's what we're really trying to optimize right now. That's pretty much my talk. Ruben, I think, really wants me to stop right now because I'm at 0. I'm going to go to a few slides of what people are doing with some of this technology. So people are doing things like in retail, just counting the number of people, seeing how busy it is in the various places. This is a different application because predominantly it's different models. If you're trying to count, like, oh, is this like, hundreds of people versus just counting the individual people, it's a different model that's underlying it. We're doing some sensor anomaly detection. It's also running on these gateways, but now the inputs are vibration sensors. That's done together with SAPI, a large paper manufacturer. Doing blurring on the edge, so actually sending out images, but making sure that on basically the gateway, the people are already cut out for privacy preservation reasons. Doing ANPR is what I was just saying. Some surface crack detection on drones, different type of hardware, but the same runtimes being installed. And we've done, but this was really small MCUs recently, like recognizing the type of coffee beans in a coffee machine, kind of using a similar setup. We'll see how that one goes. But it's kind of related to some of the people here. Let's just put it that way. That's all I wanted to share for now. I hope this was somewhat entertaining. Thank you for the interest. Cool.
Do you want to throw yourself or shall I?
No, you go and throw. I think you've had practice. So.
Maybe not in the back. I don't know if I can make it.
If you can make it to the back. Oh, there you go. Yeah.
Hey, it's working. Hello.
Well, I can hear you anyway, so that's fine.
Yeah. Fine. So, I'm curious. Modern programming languages are solving this problem by compiling to LLVM, which can compile to any platform.
Yep.
So, I'm curious, why can't you just use one of those programming languages?
Yeah, so as I said, there's loads of different, in some ways of kind of trying to tackle this problem. One of the things that I find appealing about the way we're trying to do it is that you effectively compile your runtime to the target once, but the model that you're sending, kind of the WebAssembly model specification, is the exact same all the time. So you don't need to know at the time when you're creating this model pipeline what device you're actually going to send it to, basically, or have to compile for that specifically. So I think that's one of the things that I find appealing in that sense, but,
Okay. But I guess the programming language is kind of like ONNX for LLVM, so it's also just a specification for the compiler that you, Okay, but it compiles on the device? Or?
So this is one of the tricky things is, yes, there is some kind of, so WebAssembly in some ways is the latest step of or the final step of the compilation happens on the device. So, so again, it can really be thought of this kind of intermediate format before then kind of it's finished on the device, so to say. Which also means, by the way, that if you really want to optimize for speed, you would not necessarily just kind of store the WebAssembly binary, but store the, finally compiled version that is actually on the device and run it from there. So.
All right. Who else?
Oh, yeah. No.
Hi. Thanks for the presentation. I was just thinking, you would still need the cloud infrastructure, right, to gather all the data, see the data drift, and also for the deployment of the updated models on the chips.
It's kind of an interesting kind of where, like how much new data do you want to collect to keep training, for example, and do you need the cloud infra? So the simplest way with the way kind of we put this together, if you just want to recognize license plates, by the time you've downloaded that model onto the device, you can unplug it effectively from the internet and it will keep running. But it will obviously keep running only that specific model, and it will not, get any better or whatever. It will just be this model. I do think, but maybe there's something where a lot of you would disagree. I would say that there is a lot of kind of applications of machine learning and AI models where you are not all the time trying to retrain. Actually, the people generating these models would have to collect loads of data and put in a lot of processing to create a model. But once that model is there, you might want to use it in a lot of different situations where you're not necessarily concerned in getting new data. We're trying to do some of these things now where, like, if the predictions are super uncertain, that we're capturing a frame and then either like storing that locally or sending that to the cloud so that we can use it for retraining. So we're definitely getting into some of these more hybrid modes, but right now we're really approaching the training as something that's totally separate from the using of these models.